Hello there. Today you join me with a review of an Anritsu Spectrum Analyser. This particular model goes from 9 kHz to 2 GHz, and it's the MS610C model. Is this one, and today we're just going to have a look at the general features of the Spectrum Analyser. Now we perform certain measurements with FM and AM modulation. So first of all, I'm injecting a signal from my signal generator, which is located here, over to the input, the RF input of the Spectrum Analyser at 1 GHz frequency. We've got no modulation on at the moment. We've switched the mod off. I think I've done that successfully. So we can have a look at the signal more in depth and some of the features and do some measurements. So looking at it, what's unique about this particular Spectrum Analyser, unlike the Hewlett-Packard range, is we don't have a direct frequency entry. Instead, what Anritsu have done is they've gone for a frequency control, a fine and coarse knobs here. So obviously the coarse frequency knob adjusts the coarse tune, and then the fine tune knob here, which is a multi-turn pot, gets the frequency finely adjusted. Now the reference oscillator, which is in this unit, which is a crystal oven controlled, temperature controlled crystal oscillator, does need about 30 to 40 minutes from when you turn the instrument on to warm up. So obviously from a cold instrument the frequency might start to drift. So once you lock onto a frequency, for example, you might start to see it disappearing off the end of the screen, having to keep retuning until the oscillator within the unit has warmed up to its correct operating temperature. Obviously you can use a rubidium standard, an atomic clock, a cesium standard, for example, a GPS locked frequency standard. I have an RS Components HF radio locked clock source, which is from a global clock which is broadcast around the world. I think it comes from Germany, the signal on the HF, and it's basically a box with a ferrite rod aerial on the back that picks the signal up on I think it's 10 kHz or 100 kHz or something like that on the LF bands. And because it's a time clock, then we can lock every instrument in the workshop to that, and the unit itself gives 1 meg, 10 meg and 20 meg outputs, I think, for different types of test gear that works on different frequency standard inputs. So you know, you can lock instruments quite inexpensively using you know, off-air frequency standards, for example. Now just to look into this Spectrum Analyser, we've obviously got what is the start frequency button here, so we can press this button and we can have whatever frequency we're looking at the moment moved over to the left side of the screen, and then we can select a wider resolution bandwidth so that then we can look at the radio spectrum further up as sort of a start and a stop frequency. That's one mode as well. We've got center frequency mode, so we can, for example, tune the carrier to the center frequency, or what is the dotted line in the middle, the center graticule. And when we do that, if we want to, we can widen the span, radio span, to cover the entire frequency range from 9 kHz to 2 GHz, and then we can narrow it down and down and down. So we've obviously got an input attenuator section where we can attenuate the input as well, and set the reference level with the top graticule or any graticule that we wish in the vertical plane. In the horizontal plane we can select the resolution bandwidth, the sweep, how wide a signal are we looking at. Are we looking at the whole radio spectrum, part of it? We can deal with that. Then we've got various things like, for example, resolution bandwidth, sweep, sweep time, how fast we're analysing the signal, etc. So we'll get on with some measurements and we'll demonstrate its capability and how we can make a measurement directly from the Spectrum Analyser without the use of other instruments such as mod meters, frequency counters, things like that, and how we can look at modulation and measure its deviation in case of FM and depth in case of AM, etc. So at the moment we'll just select, for example, just to give you a demonstration, with the start frequency button pressed, the carrier that was locked onto in the centre of the screen is now shifted to the left, and that basically means then that we can look at a start and a stop frequency. It's not a track gen, but it's basically where we can start at a particular known frequency, in this case a gigahertz, and depending on what span we choose here, then we're looking at now obviously 2 megahertz, so we've got what was 1 gigahertz there up to 2 megahertz higher than 1 gigahertz, and each time we increase that, eventually, you know, we can keep going up and up and up and up and up until we've got a full span. So we're looking from 9 kilohertz now to what would be 2 gigahertz, and then in center frequency mode, if that was selected again, then we'll see the 1 gigahertz signal at the left, or whichever signal or frequency we were locked onto here in the frequency counter, and then whichever we go to in the span here, we can go up in that level. So half a megahertz, 500 kilohertz higher, 1 megahertz higher, etc. Or we can go to full span, which will knock off a center frequency thing, and then we're looking at 9 kilohertz to 2 gigahertz. We've got the center frequency control back, so we should be able to adjust that span back down to something fairly reasonable, and then we can fine tune this if we just go back to center frequency and open the span up, just adjust this back to center. Now, as part of this, we've got the reference level, which can adjust the vertical plane as regards to where we're going to place the peak of a signal. For example, we can have it on the top line or 10 dBs below the top line, which is on that line there on this graphical scale. Then also we can increase the width of that signal, so we can resolve it more clearly, and that's what we're doing there with that. And then when we go back to marker level here, when we can measure the signal level as well. So the dead center of the screen with this vertical line represents the level, what the amplitude of a signal is, and it's giving us a reading there of 1.6 dBm. So that gives us the level that we're measuring at this frequency. Now, if we were to measure FM deviation when we modulate the carrier with a signal, we can then use the graphical scale as well to calculate the modulation, and that's what we're going to do now. So we're going to introduce modulation very shortly, but before we do that, I make those measurements. It's fairly easy to drive is the unit. We've got some additional filtering as well and scale. We can do single sweeps or free run, so it's in free run mode at the moment. There's line mode, video, and then the single, and when each time we press this button we can get a single sweep to take place, with a remote local button as well for if we're using GPIB mode. On the scale we can have it at 20 dBs per division, 10 dBs, 20 dBs. There's a linear mode there, and then we've also got back to 10 dBs again. We've got a video filter which can clean up the signal, so for example that's at 10 kilohertz, and then with 100 kilohertz video mode, so you'll see sharpen that up when we deal with this. With an uncal light here, which means any settings that we deal with in the instrument which make it go out of calibration, this light will illuminate. So although we can perform measurements, they might not be accurate if that light's lit, because we can make it try and do things that it's not meant to do, basically. We've obviously got not only a marker level, we've been into the reference level. We've seen that it's 10 dBs per division in the vertical plane. We've got the frequency span there, so we're at 2 megahertz. I think it is. Is that 2 megahertz? Yeah. So basically, it's 1 megahertz from the left of the screen to the center, and another megahertz from the center to the right of the screen. So the total width across the screen is 2 megahertz in this case. In addition to that as well, we've got the resolution bandwidth or the sweep set to 0.1 megahertz. So that's the bandwidth for resolving. Now, if we go back to this top again, although we're on a center span, a span of 2 megahertz, we've got the input attenuator. So if a signal's above a certain level and it's not able to be seen fully in the screen as we see there, say the bottom sections of this waveform is up here and the signal's effectively going off the top of the screen, then we can adjust the input attenuator, and we can, obviously as you can see there with the noise floor, you know, we can pull a signal out that's quite low down in amplitude and resolve that by adjusting the input attenuator. So that controls the level of signal that's coming in on the N-type there. Likewise, this has a dual mode, not only of resolution bandwidth but also sweep time. So we can, the fastest it will go to, I think in this case is, what's that say, 10 milliseconds, and then we've got 50 milliseconds, and then it starts really, you know, slowing down. So you can resolve it quite easily, the signal there. I'm not sure if I've shown the what is the marker level. Yes, I have. I remember talking about that. So that's a little rundown excuse me, of the controls with a little calibrator pot here, that when the instrument's warmed up and it's all got to a level where it's nice and snug and warm and the oscillator remains stable within it, the reference oscillator, if it's not locked to an external source that is, we can adjust this and to calibrate it so that the frequency we see here versus this aligns with what we're giving. So in other words, if we put a 1 gigahertz signal in, we know that to be correct. If this is reading dead center and this says 998 whatever megahertz, then we can adjust this potentiometer to make this read the correct frequency. So that's how we can calibrate its frequency accuracy on the readout. This is the intensity control for the monitor itself, a CRT, for the brightness. This is the RF gain as well, so we can adjust that. That's again another like a form of attenuator, where we've got again adjust. We normally have that fully to the right, and then the graticules are reading correctly, because obviously if we turned it to there and we've got it 10 dB per division, it's now not reading 10 dB per division, it's reading something like 15 dB or something like that. So we'd have that adjusted to the fully to the right. There's another connector here for a RF power probe, which is an optional accessory. And then this is a 50 ohm input jack and the power switch to the left of it. Now the 50 ohm input jack, it's quite important that when you look at that, it does actually say it can take a maximum of plus 20 dBm and no more, and plus or minus 400 volts DC. So if we were using this in a capability where we were using, say, a bias T, or we were measuring an amplifier that had a DC bias also present on the RF line, technically this can take up to 100 volts DC and maximum 20 dBm, which is not a lot of power. It's milliwatts, so you wouldn't be able to transmit high levels of power into this. If you did, you'd damage the instrument. So again, RF attenuators on the input externally, if you are using a transmitter, for example, that does many watts, you need to attenuate that signal down first before it enters the instrument, otherwise you'll damage it. So we'll do an FM measurement now, and we will then look at how it can measure FM and how we can read the frequency and the deviation level directly from the graticule. We'll do this for both FM and AM modes of transmission, and we'll show you that, how to use a spectrum analyzer in that capacity. Right, we're back. We've introduced modulation now from our signal generator, which has been fed in on the 50 ohm input, and we're going to now measure that modulation, what that would be on the spectrum analyzer. So if we alter the resolution bandwidth now, so we can pull that signal out and analyze it further, we can alter the span and the resolution bandwidth, and between both we can then pull it out to analyze better. So we use the span to try and drag that out now that we're modulating it. And you'll notice now when we look carefully at this carrier, you can actually see an envelope which is here, and it goes down and then goes back up again that side. Now I can see that with the naked eye on the CRT display, not through the camera. I can see that very clearly. However, through the camera it's more difficult for me to demonstrate it, simply because it doesn't resolve it properly through the camera. But you can just about make it out. It's this envelope there. Now these lobes there and there, which we are more or less flat in this measurement, these are sideband lobes. We don't actually include those in the measurement. We're looking at the modulation envelope, and so therefore we're looking at a signal which, instead of having the nice peak and then back again as a carrier wave, we're frequency modulating the carrier wave plus and minus to the centre frequency, and that's called FM total system deviation, or how far we move a carrier minus of the centre frequency, and also how far we move a carrier positive of the centre frequency. And this gives us what's called FM deviation, or frequency modulation, which obviously is what we're doing. We're modulating the frequency of the carrier plus or minus. The amplitude remains the same in RF amplitude, but the frequency changes this time, unlike AM, which is amplitude modulated, which was a measurement we'll do next. So we've pulled that signal out now, and we're at a 100 kilohertz total picture. So from this left side of the screen to the right side of the screen, which is here, we have 100 kilohertz deviation. So each graticule in this measurement is equivalent to 10 kilohertz. So we've got 10, 20, 30, 40, 50, 60, 70, 80, 90, 100 kilohertz. So if we will look at the envelope and how many graticules that covers, that will tell us the deviation of a FM carrier. So if we count those, if we align the instrument so that it gives us the envelope, which you can just see here, you can see the envelope. It starts in the top right hand corner, goes down to there, and then comes back up again. You can see that just about on this camera. Now on the naked eye on that CRT monitor, it stands out like a sore thumb, and you get a lot more resolution and clarity, if you like, of the waveform, that just simply doesn't show up at 60 frames per second at high definition, I'm afraid. But you can more or less see the envelope if you look carefully there. Now that covers 2 graticules wide. Okay, so we have obviously, if each graticule is 10 kilohertz wide in this measurement, I'll just adjust it back so that we can see it clearly. It covers 2 graticules, so that's 20 kilohertz deviation. Total system deviation is 20 kilohertz. So we're going plus 10 kilohertz and minus 10 kilohertz. We ignore the sidebands, which are these lobes. Anything outside the envelope going this way, we don't include that in the measurement, because these are sideband products, which you'll see on other measurements that I'll be doing, and I'll explain more about sidebands, which is a summing or a product of the signal either side. But in this measurement we're just concentrating on the envelope. So we have a total system deviation there of 20 kilohertz deviation. So basically from this far left of this graticule to the far right of that graticule is 20 kilohertz. So if we increase the deviation now, if I set the signal generator to give a modulation level on that, let's say 100 kilohertz deviation. Now we've really gone off, so we need to adjust the span again so that we can start to resolve that. And this is where we've got, which is more difficult to resolve on this. Let's see if I can see with my naked eye, but it's very difficult to see that on here. I'll just see if I can alter the sweep time to see that. Might be it's quite difficult, but basically there's a modulation envelope which I can see, but unfortunately is difficult for you guys to see. But it basically starts up here and goes down to a point here, and you can more or less make it out in the video, but it is quite difficult. And then it goes back up again this way, and so that will give us the measurement. And seeing as we're on a 1 megahertz step, we've got 500 kilohertz this half, 500 kilohertz that, making total of 1 megahertz. We can work out then what the deviation is, again with the envelope that we did before. Now unfortunately, with this camera being as it is, with the frames per second that it's giving, I can see the envelope very clearly with my naked eye, but yet it's almost impossible to see it on the camera. But I can see a distinct envelope that comes down and up, and then I can make that measurement, and it is roughly 2 graticules wide again, and obviously that would mean 200 kilohertz, because we have 100, 200, 300, 400, 500 kilohertz, 600, 700, 800, 900 and 1 megahertz, which equates to the span. And so we're covering 2 graticules again, more or less, with the envelope, and therefore we have 200 kilohertz total deviation, plus 100 kilohertz and minus 100 kilohertz deviation. Total system deviation being 200 kilohertz. So that's how you can make frequency measurements quite easily, you know, using a spectrum analyzer, as to not just the carrier frequency and the amplitude, but we can also make measurements where we're measuring the modulation deviation, and we can align transmitters as well to abide by whatever they should be giving by using the spectrum analyzer to measure that, rather than the you know, using a modulation meter or a frequency counter or whatever. So the spectrum analyzer is useful for doing all kinds of measurements. So I shall come back very shortly with the measurements in AM, and we'll look at the AM measurement now. Okay, just before we go on to the AM measurement, I found a way of being able to show the measurement we were just doing a little better by modulating the carrier with a square wave instead of a sine wave. And now we can see the products of the sidebands here quite clearly. And then we've got the modulation envelope, which is this. That's the modulation envelope there, which we can see when we measure that, where it hits these 2 graticule corners, and that gives us the total deviation of what we're looking at. Now if I adjust the sweep time, we can see a little bit more detail. Potentially I can change the span slightly again, so you know we're getting more of the picture now as to modulation. So this is the modulation envelope, this section here. So that's the measurement, that's where we measure. We don't bother with the sidebands because they're a product of this modulation, so we're looking basically from what is the flat portion, or the basically from this envelope side to that side is the measure of deviation. So that just gives you an example of how we can do that, how we can make that measurement. Okay, so I'll come back with the next one with the AM measurement and we'll look at that. Right, we've got a AM signal going in now from the signal generator. We're generating a 1 GHz signal with a 1 kHz tone, modulated at 60% of deviation. So this time what we've got a signal which is deviating in amplitude rather than frequency left and right. The carrier frequency remains constant, but it's modulated up and down in amplitude, hence the term AM amplitude modulation. Now on the spectrum analyzer can resolve this further with a combination of resolution, bandwidth and span. So we'll reduce this signal again. Let's have a look, see if we can pull it out a bit further. Oh, span, there we are. Right. So we can see the 1 kHz tone on there, and we can also just about make out the waveform that's present. You can just about see a 1 kHz tone in that ramp as it's going up there. Now if I go to the span, and let's make it a 0 span, so we're looking at basically the total modulation depth. If we go then to let's have a look here, 0.1 megahertz. I'll change the scale from 10 dB to 20 dB per division, and then let's have a look and see what we've got there. So if we were to look at this in the context of a 1 kHz tone, it's quite difficult to make out on the camera, but when you look at it on the CRT display, you can see the 1 kHz tone amplitude of a carrier is being modulated with a 1 kHz tone, and we can work out the modulation depth now because we can count the graticules. So we can more or less count 10, 20, 30, 40, 50, and that's probably around about 57ish roughly. So it's reading slightly less than what the SIGGEN says it's doing, but it's near enough 60% of the modulation in the screen. We might be able to clear it up with using some of these filters, but I doubt it very much. But yeah, certainly at that we can resolve it. Now I can reduce the frequency so that we're able to pick that sine wave out better, and I can perhaps adjust the sweep time. That's another way of being able to count it as well. But I'll just reduce the frequency, and then we might be able to pick that out better on the waveform. Okay, so now we've got a 100 Hz tone at 60% modulation. So what we're doing now is if we adjust the frequency span and then alter that, I'll explain what we're doing. We've got the amplitude of the signal modulated vertically. In other words, the amplitude of the signal will be modulated by 100 cycles a second, in this case 100 Hz. Now in order to measure the depth, we can do it looking at from here to there. We can do that, but the true modulation measurement is done by going to a 0 span. So what we do is we're effectively going to stretch that out so that both sides of the carrier wave, if you like, appealed upwards to a flat line across the display, so that we're basically taking a snapshot of that waveform there, and we're then spanning it out, so we're lifting both ends of this signal out and then reading it across the display. And so we achieve that by going to what is there a zero span, and that's what we've done. So we've homed in, if you like, on that single signal that we saw in the middle, widened it right up and lifted it to zero span. So we're just looking now at the signal itself and what modulation depth there is there. And if we change that now to a 20 dB per division scale, we can see, well, 20 dBs across the display. We can work out now the measurement. Now you can change the reference level as well to get it onto a graticule line, or align it directly with the top of a display, for example. So you can count down from the top, 10, 20, 30, 40, 50, and then 60. So the total modulation depth is 60% of the 100 which is available. So 100% is the whole carrier power, and 60% means that 60% of the whole carrier power is actually being modulated with a signal, and that's what we call AM depth. And so therefore when we look at that signal, that's how we can read the AM depth. So with FM we can see the modulation envelope when we frequency modulate the carrier. The FM measurement I did earlier was with a 1 kilohertz tone, modulating at whatever we were doing, and we measured that and we saw the envelope, the inverted envelope, and that can give us a modulation width of the frequency modulation deviation measurement. Whereas with AM we're modulating the carrier power, so one moment in time so much of the RF power is almost not there, and the next minute it's at full level. So this represents a 1 gigahertz signal that's been modulated with 60% of the carrier's power modulation. So as you can see there, the total screen is being pulled out so that we're extracting that signal. Now if I were to widen the span again, if we can get this damn thing to widen up a bit, you can see now we're looking more at the top of that signal curve, and there we are. So that's what it looks like at the top of the signal curve, and if we align that so that it's more or less dead center in the screen, and that's the depth. But we need to expand that out and drag up these sides so that we can read the whole depth, and we do that using zero span. So that's how you use zero span on the spectrum analyzer to read modulation depth of AM signals, and that's where we can get to that there. And you might need to choose a lower frequency to resolve it, modulation frequency, so you can see it physically. Now obviously if that was music or speech, that would be varying all the time, you know, it would be altering, and that's why you get a modulation envelope sometimes at certain frequencies. And speech, like on FM, would be all over the place, and music, we're using a constant frequency so we can pull it out. But if you were looking at these signals off air from say a broadcast transmitter, or an FM or AM broadcast transmitter, you'd see a widening variance of signal, and that's representing the modulation, be it music, content, speech, whatever, at all sorts of different frequencies. And we'll look at that as well in another video regarding looking at signals off air and how to represent them. Okay, we're back now with another measurement, which is about more to do with core channel interference, when we have two RF carriers that are very close in proximity. So at the moment I'm generating two RF signals very close together. This is a first signal and that's a second signal. Obviously the first signal is a bit higher than the second signal, which simulates a real world environment where we've got a receiver which is basically tuned into one frequency. Might be a higher signal or a lower signal than perhaps adjacent channels are. But what we've done with the second signal is here, slightly higher in frequency. So they are very close together. This carrier here is 1 gigahertz exactly, and that is 999.950 megahertz. We've got a span of 100 kilohertz from left to right totally, and we've got a resolution bandwidth of 9 kilohertz, so we can resolve these signals, which has picked them out quite nicely in this context. Now when we introduce FM modulation onto either of these carriers, they're going to obviously deviate, and the focus of this measurement is to illustrate what happens when deviation becomes excessive and how it can interfere with adjacent channels. And so this is what's really important when you're measuring FM deviation or transmitter. You're doing transmitter alignments. The specification for that frequency and modulation type is normally quoted by the regulatory authority in that country. So for example, in the United States it will be FCC, and in the United Kingdom it will be Ofcom. I think in Europe it's the ETSI, European Telecommunication Standards Institute, and every country has a governing body which denotes what the modulation standard will be on a given frequency when they license someone to use a radio transmitter, and also the deviation allowance for that type of channel spacing. So some radio licenses that are given out were for 6.25 kilohertz channels, 12.5 kilohertz channels, 25 kilohertz channels, etc. So for example, a 12.5 kilohertz frequency would be, for example, 433.9125 megahertz. That's a 12.5 kilohertz divisional channel, whereas a 25 kilohertz channel will be, say, 433.525 megahertz. You know, and the next one will be 25 kilohertz higher than that, and 25 kilohertz higher again, and they'll go in steps of 25 kilohertz. And normally when you get radio systems that have got, say, 25 kilohertz steps, in past years before digital systems became available, they would normally allow the deviation to be wider than what would be allowed on, say, a 12.5 kilohertz channel radio. And so generally the modulation scheme that's applied to 12.5 kilohertz channel is plus or minus 2.5 to 3 kilohertz deviation for the carrier to deviate when you speak into the microphone on a transmitter. On a 25 kilohertz channel radio, the radio is allowed to deviate plus or minus 4.5 to 5 kilohertz deviation either way, and that's because the spacing between channels, particularly on 25 kilohertz channels, is wider, and obviously we wouldn't have another 12.5 kilohertz channel in between, simply because when we introduce modulation it would spread into the adjacent channel. And so we can obviously go up in 6.5 kilohertz steps, 1 kilohertz steps, 2, 3, 4, whatever kilohertz steps, but it's just that regulatory authorities space out radio channels so that they don't interfere with one another. So for example, if this was 12.5 kilohertz away from that, we wouldn't have another channel at 6.25 kilohertz in between, simply because when we introduce modulation we get something like this. The spread of the adjacent channel, if we had a 6.25 kilohertz channel here that was being used by somebody in a radio system, the channel that was here, when that's now modulated, is spreading into that particular channel. But if you notice, it's only just spreading as well to the start of the next channel, adjacent channel, which is 25 kilohertz away. So naturally, if we were to reduce the FM deviation so it became less deviated, in other words, we were using a 6.25 kilohertz channel, which would use a 1.5 kilohertz deviation, A 12.5 kHz channel would use 2.5 kHz deviation, and a 25 kHz channel would use obviously 4.5 kHz deviation. You can see that the wider the steps are, the more allowance is given to deviation. And so nowadays we tend to use 12.5 kHz radio systems or 6.25 kHz around the world that are analog, not digital. But again, same with digital modulation schemes. The carriers modulated with either QAM, quadrupole amplitude modulation, quadrupole phase shift key and QPSK, Tetra, that's another digital standard. We use time slots, FFSK, fast frequency shift keying, all kinds of different modulation standards that are out there at the moment, Moto Turbo, all these different digital standards, P25, etc. They all have different bandwidths, different deviations, amplitude levels, and so they can quite easily spread into adjacent channels if they're not regulated and governed and the transmitters are aligned correctly. Then you can cause interference to other users in the radio spectrum. And so at the moment we've got one carrier here which has been modulated, but it wouldn't interfere with the adjacent channel at the moment. So if we were a receiver listening to this frequency, we wouldn't be interfered with. However, the moment this spreads into this, then it would interfere. And so that's why transmitters need to be aligned correctly, so they give the correct deviation levels, otherwise they'll cause interference to adjacent channels. They spread into other channels. And so, for example, if I were to use, say, for example, in this case 5 kHz deviation, we can see now that we've got back the more or less the middle portion here. And so selectivities of receivers that's quoted in the specification will tell you the selectivity of a receiver. And so that generally controlled by the bandwidth of the IF filter in the receiver section. And that's what enables us to reject adjacent channels, because sometimes these signals are a lot bigger adjacently to our channel than what our channel power is. So if we've got a big high-powered broadcast transmitter here, the signal can be massive, and that can overload the receiver anyway, even though it's not spreading into our channel at the moment, simply because the selectivity of the receiver might be quite wide, and it might be including some of the adjacent channel's power, and that can suppress our wanted signal. And so IF filters are employed, which I'll do a video on, which narrow that bandwidth. So when we're pulling out just this signal, we're obviously pulling out quite a lot of other signals with it, and we need to selectively filter out the other channels that are nearby that are having an oppressive effect because of the power of their signal is quite strong in comparison to our signal, which might be quite weak. And we need to prevent that from interfering with the receiver. So what we do is we have like a window, which is a crystal filter, that just allows that section to be pulled out. But no matter how good a crystal filter is, or a selective filter in a receiver, whether it's a bandpass filter on the front end in combination with crystal filters later in the first and second IF stages of a receiver, if the adjacent channel isn't correctly aligned with the transmitter, if it spreads into our domain, our window, then it will interfere nevertheless. And that's why we've got to be very careful with transmitters, that we don't just let stuff go out to customers, or in amateur radio fraternity when we're doing measurements on repeaters or on broadcast transmitters, for example, that we don't let the existing channel that we're occupying spread into other adjacent channels and cause interference to other users. So I can happily now introduce the modulation on the other carrier as well, and we can see there that they're quite harmonized in the fact that they can both coexist together without causing interference, because the separation between the channels is the guard band, as it's known as, is actually quite wide, and we wouldn't put another channel in the middle anyway, simply because it would be interfered with these two broadcasting at very high levels next to the main channel that we would use here. But if we've got lots of 6.25 kHz channels or 12.5 kHz channel spacing, we can get a lot more traffic in the same given frequency range. If we've got a load of 25 kHz channels, they're quite wide each channel, so therefore we get less availability in that given bandwidth or that frequency range. So the thought now, modern technology and modern radio systems use a smaller deviation, and therefore you can get many more channels. So instead of just having two here, if we were using 12.5 kHz deviation, for example, 12.5 kHz channels, sorry, then we will get more channels in that available bandwidth, and so we would effectively make the band more usable, and we can obviously get more users on it. So this is how we do it. And now, of course, if I reduce the modulation on one radio signal generator to simulate that, and we then reduce that level, then we can see that we're getting, you know, we can in theory we can use more channel capacity. So, you know, that's a good example of it. So we can narrow these effectively and then have extra channels in, so we get more channels in the available bandwidth. So that's just an example, and obviously if I were to reintroduce modulation on the instrument that we've got here, if we were to over modulate, for example, let's have a look at you. So now we're over modulating. The channel that was here has now got an excessive deviation, and as you can see, it's well into our wanted signal on the adjacent channel, and it would spread into it. So problems can occur either way. You know, you can give out interference to others, they can give interference to you, but if a deviation's too wide because the transmitter's not been aligned correctly, it will impact on adjacent channels. So that's an example of what can happen, and obviously the more we reduce that, the less of an impact it has, and thus, you know, we don't produce interference to others. So this is the importance, highlights the importance of being able to get the correct alignments done on radios and transmitters. And this is why these telecommunications governance government departments have investigation departments that go out and investigate known source of interference, so that if radio users such as emergency services, broadcast radio for example, or you know, aircraft or whatever in the airband get interference from other sources outside the frequency band, through harmonic interference or through co-channel interference, because there's a transmitter which is not behaving itself, then those sources of interference need to be found and then rectified. And so this highlights the reason why we don't want excessive deviation in a system. So if we over deviate, we interfere in adjacent channels, and that's a good example there of over deviating into an adjacent channel. So that's a little rundown on that. Okay, so now we can look at a measurement for harmonics, and this is a perfect illustration of harmonic production from a signal generator. So right now at the moment we've got a frequency which I'm generating. The fundamental frequency is here at 300 megahertz, which has got the largest amplitude. Now we've got then, as we can clearly see, a first, a second and a third harmonic. And with harmonics in the radio spectrum, we obviously get multiples of the frequency. So this is 300 megahertz. So the first harmonic is twice the frequency of the fundamental. So this is 600 megahertz. And then obviously the second harmonic, which is here, is again 300 megahertz higher than 600 megahertz. And then the third harmonic, which is here, which is smaller, and generally they are, is 300 megahertz higher than that. So you can see from a transmitter, what we need to do is we need to suppress out these harmonics, because obviously if we've got a radio system being used on the same frequency at 600 megahertz as this is interfering with, then it will cause out of band interference. So although we're happily transmitting down here at 300 megahertz, whatever we're doing, we could be broadcast radio, we could be an aircraft, we could be a radio amateur, taxi service, we could be a security system, you know, that's been used, video transmitter, whatever. If we're broadcasting down here, we don't want to be interfering up the band, nor do we want to be interfering down the band. And transmitters often employ, in their final output stages, bandpass filters, and indeed external of a transmitter as well, separately. You can connect what we call cavity filters, which can be tuned precisely to those frequencies. And we often get problems with harmonics at hilltop radio masts and repeater sites, because we've got several broadcast transmitters or several transmitters going, or 10, 20, 30 transmitters, depending on how many antennas on the radio tower, and they can all produce mixing effects between them. When you're broadcasting a signal off of multiple antennas in similar frequency bands, they can mix together the signals and produce all sorts of weird harmonics, which can then interfere with the receivers within the equipment cabin at the bottom of the hilltop radio tower. It can cause all kinds of problems. So generally when you go to hilltop radio sites, you'll not only see the transmitters and the receivers there, or the repeater units, you'll also see a bank of cavity filters and tunable filters for the antennas, and that's to reject harmonics that not only the transmitter might be putting out, but also to prevent interference as well from other transmitters which are on the site, which just the close proximity of the antennas on the mast, plus the mixing effect sometimes of mixed services, or what they call multi-tenanted transmitters, where we have multiple users on the same site. It can cause all kinds of radio interference, cross interference, localized interference, all kinds of problems. And so generally in transmitters we have bandpass filters which reject these harmonics, and a specification in a transmitter, a service manual, might say, for example, that harmonics have to be 80 dBs, for example, below the fundamental. And so when we measure this level here, we expect, according to the specification that's given in the manufacturer's manual, that the first harmonic must be 80 decibels below the fundamental. And that means then that the bandpass filter is working properly. You can't totally reject harmonics. To some extent you can, depending on how good your radios are, but generally speaking it's accepted that first, second and third harmonics have to be a certain dB below the fundamental frequency. And the reason for that is because when we're dealing with very high powered transmitters, even though these might be very low power insofar as the main carrier is concerned, the signals here can radiate quite far and wide off an antenna and cause interference over a wide geographical area. And so by suppressing these to such low levels reduces that possibility, and that's before it leaves the transmitter. Once it's left the transmitter, then we can introduce a next stage of filtering to totally eradicate them altogether, which are these bandpass filters I've been mentioning, or cavity filters, tunable filters, etc., duplexer filters. All kinds of different filters can be employed to get rid of these. So we don't want these to be high powered harmonics, we want these to be minuscule in RF level, so that, God forbid, there isn't any filtering and we connect to an antenna, these harmonics can't escape very far beyond the radio site to then cause interference to a wide geographical area, because on these frequencies could be television signals, there could be emergency services, aircraft, and you could then cause interference to a whole number of different services. And so the expectation is that the regulatory authorities produce a specification to manufacturers to say that we expect your radio equipment to meet this certain specification in regards to harmonic suppression. And what we tend to find now in the modern world with China and its emergence into manufacturing of radio technologies, etc., a lot of these cheap Chinese radios have very high harmonic content, and thus they have a potential to cause interference to other radio users. And this is why, it's very difficult sometimes for the regulatory bodies, such as the FCC, Ofcom, ETSI, whatever, to regulate, which they used to be able to do quite well, regulate the import of radio equipment from parts of the world where this type of issue isn't simply an issue as far as distribution or export of radio equipment. So although radio might be cheap, it might be cheap because, if it comes from China, for example, there's a well-known radio manufacturer in China many years ago called Yingtung, and they made radios for the amateur radio market, but they also could do PMR radio frequencies for private mobile radio users or commercial users, and they would actually produce horrendous harmonics which no end of times caused interference to other radio users elsewhere in the radio spectrum. And the harmonic level was so high that there was a fair percentage of the transmitter power also on the harmonics. So if this was 5 watts from a handheld, for example, the first and second harmonics may have been 1-2 watts output, so therefore the harmonic level was not suppressed enough to prevent interference to the radio users, and that's an extremely dangerous thing, and that's why it's very important to regulate radio manufacturers to make sure that they employ the correct circuitry, that they analyse and test the radio. The radios have to be sent off for a testing house, for example, to be individually or independently certified that they meet the specification of that country, and they get a certificate of compliance, and therefore, when you buy a radio for marine use, airband, for private mobile radio, for commercial, whatever, that that radio is going to operate without causing interference to other users. And sometimes we forget that when we're looking at these cheap radios from places like China, and it's not until you connect one to a spectrum analyzer like this that you'll then see evidence of extreme harmonics, which can cause all kinds of problems. And so that's what needs to be looked at when you're looking at radio transmitters as well, is not only the channel spread and the deviation, the modulation characteristics, but also the harmonic content and the interference that can cause to the radio users. Now, in this context, the fundamentals are a lot higher than the harmonics, and as you can see, each time we get a harmonic it gets less in level. That's not necessarily the case with some transmitters. I've seen transmitters where the third harmonic is nearly as high as the fundamental, and this is very important as well when we're dealing with high-powered transmitters, such as broadcast transmitters. We've got a television transmitter, for example, that's doing 100,000 watts of RF power, even though the specification in the manual might say that the first harmonic has got to be 80 dBs below the fundamental. Even though it might be 80 dBs below the fundamental, if you're transmitting at 100,000 watts on the fundamental frequency, the first harmonic might have several kilowatts, several thousand watts at that frequency. And so if we were to broadcast that off an antenna, particularly high altitudes, which TV transmitters are normally associated with hilltop, huge structures, thousands of feet tall, that signal can cause massive interference across the country. So, you know, you can actually lead yourself down all sorts of problems. The bigger the power, the bigger the harmonics will be, naturally. But we take drastic measures in broadcast technology to suppress these carriers, and there's many millions, if not billions of pounds spent in the broadcast industry, for example, the people that make television transmitters, FM broadcast transmitters, etc., to suppress these harmonics and totally eradicate them. And naturally that's a very expensive job, particularly when we've got transmitters that are broadcasting up to 1 million watts of RF power, or hundreds of thousands of watts of RF power. It becomes quite a technical challenge to get rid of harmonics and other intermodulation products, particularly where we've got a vision carrier and a sound carrier, and the mixing effects or the intermodulation products, the IPs as it's known as, that mix together, that can create other kinds of harmonics which are to do with modulations mixing together. And so it becomes a science in itself, just trying to get rid of harmonics that are derived from the fundamental carrier. So again, that's just an example, albeit a short one, of a typical harmonic relationship to the fundamental. And so that's a little rundown on harmonic interference. Okay, so having done a little review of the instrument, yeah, I'd just like to say it's a nice instrument. You know, they're very well made. Anritsu is a very good brand, obviously, been in the market for many years. Although it's not got the bells and whistles of some of the more modern spectrum analysers, you know, such as the HP Agilent range, some of the, you know, the Aeroflex kit and Marconi spectrum analyzer, etc. You know, you don't need that really. I found it very simple to use. It's good as an entry-level spectrum analyzer. You know, it doesn't have all the fancy bells and whistles that you see on spectrum analyzers, such as the, you know, the HP Agilent one there, for example. But sometimes instruments can become too complicated, and you know, you sometimes you need a degree in order to be able to work them, because there's menus within menus within menus, and secret menus and sub menus, and you know, it can get quite annoying when you're trying to do a quick measurement, just something basic. And some instruments are more difficult to drive than others. This is very simple and quite easy to use, very clear and concise, and you don't need to faff about with it. You know, it just does what it says. You know, you want it to read, it'll read. And I like the knob as well. It's nice that you can just tune the signal using the knob instead of having to try and guess what frequency it is and have data entry keys. And you know, on some of the HP spectrum analyzers, they're so annoying when you know, if you find or track a signal and then you alter the bandwidth, it'll then disappear off onto some other signal that's internally generated, and before you know it, it's changed its frequency onto an internally generated birdie frequency, or an harmonic that's internally generated within itself, and it's locked onto that. And then you're trying to do a measurement and you've not realised that, and it can then confuse you in the fact that the measurement you're doing isn't the frequency that you're looking at. And I've had that happen to me quite a lot on HP spectrum analyzers. It seems to be a bit of an issue with their markers for tracking. So again, you don't get that problem with the Anritsu. It's very, very well suited, very nice to operate. On the side, we've got the carry strap as well. We've got frequency calibration hole there for calibrating the internal crystal oscillator as well, to put it on frequency. There's a foldable, collapsible stand underneath. On the rear of the instrument, we've got some sockets which we can have a look at. So we've got what appears to be, I think it says first local oscillator output and second local oscillator. So we can feed these off to other instruments, for example. We can also feed them off to other spectrum analyzers if we need to. There are various measurements that we can do through these ports. That's out the scope of this video, but basically there's an option there for further expansion. The reference level adjuster here allows us, as per this table, to measure things in dBm, dB microvolts and dBUs. So this is set to dBm 0. I'm not sure what the panel backup on and off is. I've no idea what that is. I'll have to look in the manual. Not something I've seen on other spectrum analyzers. This is a cal output at 50 megahertz at whatever dBm that says, now minus 30. I think that's a calibration port for the power probe that plugs in the front. If you remember earlier in the video when I showed the front panel, there was a gold coloured MCMX socket, I think it is, which the power probe connects into. I think that calibrates the power probe. And then for plotters and tracking generators that we can drive externally, we've got an X and a Y output, a Z output, and then we've got another, what appears to be an optional accessory to some kind of an Anritsu specification. It says control out to MS610B. I'm not sure what that is. We've also got an external DC socket here, so it can run off battery supply, an earth terminal, an IEC plug. This is a 240 volt model, so presumably for other countries there is a 110, 120 volt version. So, you know, using these outputs, for example, although this particular spectrum analyzer doesn't have a tracking generator in it for measuring filters, etc., you can use these outputs to drive plotters, tracking generators. You know, external track gen can feed off these outputs so that when the spectrum analyzer is sweeping from left to right of the screen, it'll drive the tracking generator to also sweep as well with it, so that then you can turn it into a tracking gen as well. So there's all kinds of little things that you can do with it. You know, it's fully featured, obviously. So yeah, very good instrument. I fully recommend them. You know, if you wanted to get into RF measurements using the spectrum analyzer, it's a nice sort of entry level spectrum analyzer. It's well made, obviously, a reliable brand, standing many good years of work. And yeah, so that's a review of the Anritsu MS610C spectrum analyzer, and you've seen it work in its various measurement capability, and at least now you're a little wiser as to what kind of measurements you can take or make with a spectrum analyzer. So thank you for watching the video. If you like it, please subscribe. There'll be more videos coming with a lot more interesting topics, and thank you for watching, and we'll see you in the next one. Bye now.